Hi, this is Dr. Bay, and here's Bugsy. And today we're going to talk about the second part of SN2 mechanisms. We'll delve into different kinds of leaving groups, the structure of electrophiles, nucleophilic strength, and solvent effects. So stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Just as a review from last time, the SN2 reaction is a concerted or one-step mechanism where the nucleophile attacks the carbon at which the leaving group is attached to, and then the leaving group leaves. SN2 reactions are a direct displacement of a leaving group with a nucleophile. These reactions result in inversion of stereochemistry if the initial electrophile was chiral, and its rate depends on the concentration of both the electrophile and the nucleophile. There are a bunch of different kinds of leaving groups, but the good leaving groups are the conjugate bases of strong acids. Shown below is a list of leaving groups ranked from poor leaving groups on the right side to good leaving groups on the left side. For example, iodide or I- is the conjugate base of a very strong acid HI, making it a weak base. Recall that weak bases are more stable anions, which makes I- an excellent leaving group. On the other hand, a hydroxide ion, or HO-, is a relatively strong base, which makes it a less stable anion. That makes the hydroxide ion a poor leaving group. Now let's talk about the structure of electrophiles. The rate of an SN2 reaction is most sensitive to the number of substituents at the alpha carbon. Let's look at the alpha carbon in the molecules below. How many beta carbons is the alpha carbon bonded to? The alpha carbon is the carbon that the leaving group, in this case bromine, is attached to. Starting from the left side, this molecule has 0 beta carbons, so that means that this is just a methyl group. In the second molecule, the alpha carbon is connected to 1 beta carbon. This means that this is a primary carbon or alkyl halide. In the third molecule, the alpha carbon is bonded to 2 beta carbons, which means that this is a secondary alkyl halide. And in the last molecule on the right, the alpha carbon is bonded to 3 beta carbons, which means it's a tertiary alkyl halide. Now that we have the vocabulary of alkyl halides down, we can rank them in terms of their reactivity and specifically an SN2 reaction. SN2 reactions are most reactive with methyl groups and primary substrates. They're slower with secondary substrates and are completely unreactive for tertiary substrates. But why is that? Well, SN2 reactions are governed by steric factors. Basically, think of two yoga balls colliding with one another, and that clash is signified by two blue arches shown here. For the nucleophile to approach the alpha carbon of the electrophile, it needs a lot of space to do this. To understand this in a more chemical setting, let's take a look at the SN2 transition states for each type of electrophile that we just discussed. Circled in pink is the HO- nucleophile approaching the alpha carbon 180 degrees apart from the bromine leaving group. In the methyl substituent, we see that there are no collisions between the OH group and the 3 hydrogens bonded to the alpha carbon, since hydrogens are pretty small atoms. But as we increase the number of beta carbons, you start to see the number of steric clashes increase. That's why secondary substrates undergoing SN2 reactions occur very slowly, while tertiary substrates can't react at all just because there's way too much steric hindrance between all 3 beta carbons with the incoming nucleophile. Electrophiles in SN2 reactions are also sensitive to what's called beta branching, which essentially just means more carbons are connected to the beta position rather than the alpha position. If we compared all four of these substrates, technically each of their bromine leaving groups are bonded to primary carbons, making them all primary alkyl halides. However, they differ in the number of carbons bonded at the beta position. The more beta branching, the slower the SN2 reaction, and this can be qualitatively seen in the amount of steric hindrances at the transition state because now the electrophile not only is blocking the nucleophile from coming in, but it's also interfering with the leaving group leaving. Another component that you have to consider in a reaction is the type of solvent it's in. A solvent is a liquid or solution that you would dissolve your reactants in. There are two types of solvents that you should be aware of. The first one is polar protic solvents, which are solvents that are hydrogen bond donors. Remember that hydrogen bonds are H's bonded to either F, O, or N. Some examples of polar protic solvents are water, ethanol, and acetic acid because they all have a polar OH bond within them. The second type of solvent is polar aprotic solvent, which are solvents that do not have hydrogen bonds. Two common examples are dimethyl sulfoxide, or DMSO, and dimethylformamide, or DMF. These solvents are still polar because there's a difference in charge between the O and the S in DMSO, but they are aprotic because they do not have any hydrogen bonds. Here's a more comprehensive table of different kinds of solvents. On the left side are polar protic solvents, and on the right side are polar aprotic solvents. Feel free to print this out or take a screenshot of this chart for use in future reference. So, how do solvents play a role in SN2 reactions? Well, the most common and most reactive type of SN2 reaction involves a strong negatively charged nucleophile, a good leaving group, and a polar aprotic solvent. Here's an example of methyl iodide reacting with various nucleophiles in two different solvents. In methanol, which is a polar protic solvent, and in DMF, which is a polar aprotic solvent. Note that the reaction is much faster in DMF as exhibited by large relative rates shown in the third column, and you can see how much the reaction rate has increased in a polar aprotic solvent in the fourth column. So far, we talked about how leaving groups, electrophiles, and solvent affect SN2 reactions, but there's one more factor we still need to discuss, and that would be nucleophiles. Nucleophilicity is a kinetic property measured by the rate at which a nucleophile causes the SN-type reaction to occur. But nucleophilicity is oftentimes confused with basicity. Basicity is an equilibrium property measured by the position of equilibrium in acid-base reactions. But one thing to point out is that all nucleophiles are also bases, so you'll see comparisons between the two throughout the rest of the course. Now let's go over a few different trends for comparing nucleophile strength. Trend number 1 says that within a period or row in the periodic table, nucleophilicity increases from right to left. So in period 2, fluoride is a stronger nucleophile than OH-, NH2-, or CH3-. And that trend is the same as seen in period 3. Trend number 2 says that given the same nucleophilic atom, anionic nucleophiles are much stronger than their neutral nucleophiles. Trend number 3 says that given the same nucleophilic atom, the stronger the base means the stronger the nucleophile. For these bases, we can turn to their conjugate acids and determine their pKa values. A strong conjugate acid means its base is weak, and vice versa. So there are a few exceptions to trend number 3. Typically, a strong base equals a strong nucleophile, unless it's sterically hindered. In this chart, we've listed 3 bases and nucleophiles to compare. The top butoxide ion is both a strong base and a strong nucleophile as indicated by its pKa value. The middle molecule is called tert butoxide ion, which is a strong base, but it's not a strong nucleophile because it's sterically bulky. And the last molecule is a nitrile ion, which is not a strong base, but it's a strong nucleophile because it's not sterically hindered. And with that, here's a table of good, moderate, and poor nucleophiles that you can print or screenshot for your reference. In summary, what we learned today is that SN2 reactions prefer to have electrophiles that are either primary or secondary alkyl halides with a good leaving group. Its nucleophiles should be good nucleophiles with a negative charge, and SN2 reactions prefer to be in polar aprotic solvents.
Organic.